Alright, so here's a video on 5.3. This section is about the fundamental theorem of calculus, which has two parts. Here's the first part. It's about if you have a continuous function, and I'm going to define a second function in terms of the first function, where the second function g of x is the integral from a to x of f of t dt. Sorry, I messed up a little bit when I was writing this. This should be f of t dt. Then that function, g of x, is also continuous on the interval from a to b, and it's also differentiable on the open interval from a to b, and the derivative of the second function is the first function. So g prime of x is f of x. So this is establishing a connection between derivatives and integrals. If g is the integral of f, then f is the derivative of g. Part 2 is kind of roughly saying the same thing. It's that if you have this integral from a to b of little f, that it's an antiderivative. It's antiderivative of b minus antiderivative of a, where capital F is any antiderivative of little f. Okay, so let's do a couple of examples where we use this. So the first one is to find the derivative of this function. This is not looking like anything we've been asked to take the derivative of before, but what we have is part 1 of the fundamental theorem of calculus. Of course, yeah, let's not be confused by which one we're calling f and which one we're calling g. The point is, I want to take the derivative of this function that's defined to be an integral. It's the integral from 1 to x, just the same way that this is an integral from a to x. If you're in this situation, I can tell you the answer is very, very easy. F prime of x, it's just this function on the inside, but I replace t with x. So it's just e to the sine x. So that this is, if you know what you're doing, this is the easiest question in the world. You just copy this down and you put x instead of t. Let's do one that is not quite as easy. What makes this more difficult is that instead of just going from a fixed number to x, now this and this are both functions of x, and the top one isn't just x, it's x squared. So here's how I would suggest we do that one. We're going to sort of combine parts 1 and parts 2 of the fundamental theorem of calculus. Here's what we can do. I'm going to let, and usually I use a capital letter, I'm going to use capital G to be, actually, well, yeah, why not? Why don't I use capital G? Capital G is going to be an antiderivative. Antiderivative of the inside function. Or actually, maybe I should call it g of t, because the inside variable is t. So when I say that, what do I mean? I mean the derivative of this is this. That's what it means for this to be an antiderivative of this. That means if I took the derivative of this, I would get this. Now it's easy for me to rewrite little g. Little g, how do you do, okay, so now I'm looking at part 2 of the fundamental theorem of calculus, which says in order to evaluate an integral, what I can do is I can find an antiderivative of the inside function, and I can just evaluate it here and here. So little g of x, if I found an antiderivative of this, which well, I haven't really found it, but I've given it a name. I've called it big G. What I would do is I would take that antiderivative and I would evaluate it here, and I would subtract. In other words, I plug in B, I plug in A, and I subtract. So I'm going to do G of the top number minus G of the bottom number. Right? Okay, so where am I going with this? The question was to find the derivative of little g, and I still haven't found that. I've found an alternate formula for little g, but I haven't found its derivative. So let's find its derivative. How would I do the derivative of this? Well, I can use the chain rule. This would be g prime of x squared times the derivative of the inside, right? Minus, and then this one will be similar, g prime of sine x times the derivative of the inside, right? Now, I know what g prime is. G prime is this. So, g prime of x squared would be this. G prime of sine x would be this. So then we're good. So that's how you do one like that. And you'll have a few like that where you just have different like functions of x down here and down here. But you can follow these exact steps to do those. Okay. Now let's, probably this is the more useful part of the fundamental theorem of calculus. We're going to evaluate some integrals. I forgot to write dx here. Notice when we write an integral, there's always d something. Typically, this just means the variable that we're doing. So if these are in terms of x, then this is in terms of x. And when I talk about an antiderivative, it's an antiderivative with respect to whatever this variable is. So we're going to evaluate this using part 2 of the fundamental theorem of calculus, meaning I'm just going to find an antiderivative of the inside function, and then I'm going to plug in b and plug in a and subtract. So here's how we do this. I'm going to write an antiderivative, and we know some antiderivative rules already. The antiderivative, the way you do a power of x is you raise the power by 1 and then you divide by that same number. So x squared becomes this. X is like x to the 1, so I treat that the same way. That becomes x to the 2 over 2. 1 just becomes x, right? The derivative of x is 1, so the antiderivative of 1 is x. Okay, so now let me pause for a moment. Normally, if I was trying to find the most general antiderivative, I would write plus c. But I'm not trying to find the most general antiderivative. In fact, if I look at what part 2 says, f is just any antiderivative. So I don't have to write plus a constant. I can just leave it like this. This is an antiderivative of this. So what I do, and this is typical notation for when you're evaluating an integral, I wrote down the antiderivative. This notation is telling me that I'm going to plug in 2 and then I'm going to plug in 0 and subtract, because that was the plan all along, right? That was the plan all along. We were finding the antiderivative, and then I was plugging in the top number, which was 2, I was plugging in the bottom number, which was 0, and I was subtracting. So this bracket, and notice there's no open bracket for this closed bracket. It's a funny looking thing, but this is just how the notation that we use to tell ourselves that I'm about to plug in this number and then plug in this number and subtract. So here I go. 8/3 minus 4/2 plus 2. I would subtract. And of course, I'm using parentheses here because if I don't, then I'm afraid I'll forget that I'm subtracting everything. Like this minus sign should really distribute to anything that's inside these parentheses. Of course, then I realize my life is a lot easier and I don't have to worry because everything in here is just 0, so this has no effect on anything. Anyway, oh, and that's nice. So this and this just cancel, so I guess I just get 8/3. Okay. So let's try a couple more. They're not going to get much worse than that for us right now. The worst thing you would have to do right now is a little bit of algebra. Like this one. When I'm doing a product, if I was doing a derivative, I would have the product rule, but I'm not doing the derivative. I'm doing an antiderivative. I don't have a product rule for antiderivatives. However, what you can do is you just multiply this out. I get u squared. Let's see. I would have a minus 7u and a plus 3u, so minus 4u. So I get that. And then I do the rest the same way. I'm doing the antiderivative, so u cubed over 3 minus 4u squared over 2 minus 21u. Yeah, and then 1/3 minus, this would just be 2 minus 21, because that's when I'm plugging in 1, and then when I'm plugging in 0, everything is 0. Oh boy, and then this is 1/3 minus 6/3 minus 63/3, which is negative 68/3. Okay, let's do one more. This one is, when we simplify it, let's see, root x is x to the 1/2, and if I'm dividing by that, then I'm subtracting that power from everything. So 2 minus 1/2 would be 3/2. 1 minus 1/2 would be 1/2. This would be 3x to the minus 1/2, because this didn't have any x's, and I'm dividing by x to the 1/2, so that becomes x to the minus 1/2. Yeah, so we simplified it, and now I can use the rules for powers of x. So 3/2 plus 1 would be 5/2. 1/2 plus 1 would be 3/2. Negative 1/2 plus 1 would be positive 1/2. Yeah. And then this is, let's see, 2/5 times 3 to the 5/2 minus 2 times 2/3, 3 to the 3/2, plus 3 times 2. Notice I'm doing the reciprocals of the fractions in the bottom as I go. 3 to the 1/2. So that's the result of me plugging in 3 everywhere, and then I'm going to subtract the result of me plugging in 1 everywhere. So 1 should be easier because 1 to any power is 1. So this is just going to be 2/5 minus 4/3 plus 6. And let's see if we can simplify this at least just a little bit. 2/5, 3 to the 5 halves, minus 4/3, 3 to the 3 halves, plus 6, 3 to the 1 half, minus, let's see here, 2/5 is, so I want to do everything in 15ths. So this would be 6/15 minus 20/15 plus 90/15. So 6 minus 20 is -14. So 76/15. So it's not the prettiest answer, but it is what it is. And that's the worst that it will get for this section. You just have to be willing to do a little bit of algebra and then use the antiderivative rules that we know.